Welcome to another module of this course, Computer Aided Power System Analysis. Till the last lecture, we have looked into the Newton-Raphson load flow method in the polar coordinate. Today onwards, we will be looking at the Newton-Raphson load flow method in the rectangular coordinate. And we have already explained what is actually mean by rectangular coordinate as well as the polar coordinate. So, we start today. So, today is NRLF in rectangular coordinate. So, when we say that NRLF in a rectangular coordinate, we denote, for example, VI, that is the ith bus voltage, complex bus voltage is given by, we have already seen, VI angle theta I. So, it can be written as EI plus JFI, where EI is VI cos theta I and Fi is Vi sin theta I. The basic concept is that if I have an Argand plane, is a plane. So, in the complex plane we do represent the voltage vector Vi, this is a complex voltage vector. So, this is the magnitude and this is the angle. So, then when we do represent is Vi angle theta I. So, this is nothing but the standard polar representation, but then when we do resolve this into the two coordinates. So, this is the, and when we do resolve this into two coordinates. So, this is EI and this is Fi. So, when we are actually resolving it into two coordinates, one across the real part and another across the imaginary part, this is nothing but the rectangular coordinate representation of the bus voltage. Now, what we have is, we know for any bus II is nothing but the II is nothing but the injected current at bus I, N is the number of bus and Yik is nothing but the element of the Y bus matrix corresponding to ith row and kth column. Now, according to this rectangular representation, we have Vk, we represent as Ek plus Jfk, and Yik we represent as Gik plus Jbik. So, this is, so please note that we are also representing the elements of the bus admittance matrix, which are also themselves complex quantities also in the rectangular coordinate. So, then therefore, we can write down II, let us say that it is AI plus JBI, that is we are also representing II as II in the rectangular coordinate, of which this real part is AI and for which this imaginary part is Bi, that is equal to given by k is equal to 1 to n Gik plus Jbik into Ek plus Jfk. So, then therefore, we can write down Ai plus Jbi is equal to k is equal to 1 to n, we write Ek Gik minus f k b I k plus j k is equal to 1 to n E k b I k plus f k g I k. E k b I k plus f k g I k, and this is E k g I k minus. So, then therefore, we have a I, that is the real part of the current can be given by k is equal to 1 to n E k g I k minus f k b I k, and b I can be given as k is equal to 1 to n E k b I k plus f k g I k. So, these are the expressions of the real and imaginary part of the injected current V I. Now, we know complex power at bus I S I, that is P I plus j q I, that we know as V I into I I star, that we already know. So, then therefore, this can be written as E I plus j f I star would be A I minus j b I. So, then therefore, we can write down P I plus j q I is equal to A I E I plus f I b I plus j f I A I minus E I B I. So, then therefore, P I is equal to E I A I plus F I B I. Now, we do substitute the expression of A I and B I. So, it is E I into E k g I k minus F k b I k. So, E k g I k minus F k b I k plus F I b I is E k b I k plus F k g I k. So, it is E k b I k plus F k g I k. So, it is E k b I k plus F k g I k. So, this is this, and similarly q I from this expression F I A I minus E I B I. So, then therefore, k is equal to 1 to n F I into A I is this E k g I k minus F k b I k minus E I, and b I is E k b I k plus F k g I k. So, then therefore, these are the two expressions of injected real power at bus I and injected reactive power at bus I in rectangular coordinate. Now, what happens is now we have to look at that what are the unknowns and known quantity in the rectangular coordinate. So, after we do this, so now we have to look at what are the unknown quantities. What are the unknown quantities? Now, we have got different types of bus, slack bus, then PV bus, then PQ bus. Now, in the slack bus, we always define what is the voltage magnitude and the angle. So, then once we know the voltage magnitude as well as the angle, so then therefore, its real part as well as the imaginary part of the voltage at slack bus is known. So, then therefore, there is no unknown. So, in slack bus no unknown. In the PV bus what we have? In the PV bus we do specify bus voltage magnitude and the injected real power. Now, we do not at all specify the angle. So, then therefore, because we do not specify the angle, so then therefore, in a PV bus both the real part as well as the imaginary part are unknown. For example, if I have a plane and if my bus voltage magnitude is let us say 1 per unit, and if I do let us say draw a circular arc having let us say 1 per unit for example, and so then therefore, bus voltage magnitude can be anywhere like this, can be anywhere. Each of these bus voltage magnitude is maintained at 1 per unit, but for this bus voltage, but for this vector our real part is this and the imaginary part is this. For this vector our real part is this and my imaginary part is this, and for this vector my real part is this and my imaginary part is this. So, then therefore, what happens, even though my bus voltage magnitude is maintained at 1.0 per unit, but depending on its angle both the real part as well as the imaginary part will vary. So, then therefore, even though we do pre-specify the bus voltage magnitude, but because we do not pre-specify the bus voltage angle, so then therefore, both EI and FI are unknown. So, then therefore, in PV bus, at every PV bus EI and FI are unknown. And at PQ bus we do only pre-specify the real power as well as the reactive power. We do not pre-specify neither the bus voltage magnitude nor the angle. So, then therefore, both EI and FI are unknown. Now, let us see what is the total number of unknowns. Now, for that again we take our same assumptions or other, that we have got an n bus system, there are m generators, bus 1 is the slack bus, bus 2 to m are PV, the standard whatever you have been doing m plus 1 to P q. So, then therefore, here the unknowns would be, the total number would be 2 into m minus 1, and here the total number would be 2 into n minus m. So, it is total, it is 0. So, then therefore, my grand total is, grand total is 2 n minus 2, that is 2 into n minus 1. And for PV bus, this I varies from 2 to m, and for PQ bus this I varies from m plus 1, m plus 2 to, so this you all know. Now, this result is also quite obvious to determine, because you see, except at the slack bus, at all the other buses both the real part as well as the imaginary part are unknown. So, then therefore, if I have total number of buses in the system is n, so then therefore, at each of these n minus 1 buses both the real part as well as the imaginary part of the voltages are unknown. So, then therefore, at each of these buses there are two quantities which are unknown. So, then therefore, a total of 2 into n minus 1 number of unknowns are there for an n bus system, because at each of these n minus 1 buses there are two quantities which are unknown. So, these are the unknown quantities, and we have also specified this. So, now let us look at what are the known quantities. So, now our task is to known quantities. Now, what are the known quantities? Now, the known quantities are, so far, at PV buses there are Pi are known, and at PQ buses Pi and Qi are known. So, there are total of m minus 1 and there are total of 2 into n minus m, because there are total of n minus m PQ buses, and each of these buses there are Pi and Qi are known. So, therefore, total known quantities would be 2 into n minus m, and my total number of PV buses is m minus 1, and at each bus I know Pi. So, then therefore, there are altogether m minus 1 known quantities. So, as again we note that for all I varies from 2 to m as usual, and for this I varies from m plus 1 to n. So, then what is the total number? Total is, it is m minus 1 plus 2 n minus 2 m. So, then therefore, it is 2 n minus m minus 1. So, now what happens? I have got unknown quantities which is equal to 2 n minus 2, and my known quantities are only 2 n minus m minus 1. So, then therefore, there is a deficit of 2 n minus 2 minus 2n minus m minus 1, that is equal to m minus 1 known quantities. So, then therefore, what we need? I still need m minus 1 known quantities, because otherwise I cannot solve this set of equations, because in this case what is happening? We have got total 2n minus 2 unknown quantities, but our known quantity is only 2n minus m minus 1. So, then therefore, there is a deficit of m minus 1 known quantities. Now, from where this m minus 1 equations will come? This m minus 1 equation will come from the fact that at each of these PV buses we do know the bus voltage magnitudes. So, then therefore, at each and every PV bus, this bus voltage magnitudes are given by at each PV bus we know Vi square is equal to Ei square plus Fi square. So, this is nothing but the bus voltage magnitude, this is the real part, this is the imaginary part. So, then at each and every bus these equations hold good. So, then therefore, these equations together, this is for I is equal to 2 to m. So, from here we get extra m minus 1 equations which are required. So, then therefore, to summarize, my unknown quantities are Ei and Fi. So, this is for all I is equal to 2 to n, and my equations Pi for all I is equal to 2 to n, Qi for all I is equal to m plus 1 m plus 2 to n, and Vi square equation, that is all for all I is equal to 2 to m. So, the total number of unknowns, if we do note, so the unknown here is n minus 1, here is unknown n minus 1. So, total is equal to 2n minus 2. Here the total number of known quantities is n minus 1. Here it is n minus m, and here it is m minus 1. So, total is equal to n minus 1 plus n minus m plus m minus 1. So, that becomes equal to 2n minus 2. So, then therefore, the number of unknowns and number of equations, they are exactly matched. Total number of unknowns is 2n minus 2, total number of equations is also 2n minus 2. Now, if we do recollect our discussion of Newton-Raphson polar method, what we do find that in our Newton-Raphson polar method, recollect NRLF polar. So, in NRLF polar, what we had? We had equations as J1, J2, J3 J4 as delta theta vector delta V vector is equal to delta P vector delta Q vector. That was our equation what we have seen. These equations we have found out from the linearization of the all these nonlinear equations around an operating point, or rather at some operating point x naught. So, now here in this, now this J1, J2, J3, J4 are nothing but this, I mean Jacobian submatrices, but here what we need to note down is that here our unknown quantities are delta theta and delta V, and my known quantities were P and Q. So, then what we had got? We had got actually two unknown vectors theta and V, and we also had got two known vectors P and Q. So, then therefore, this has got, let us say, two unknown vectors, and this has also got two known vectors. So, then therefore, 2 into 2, that is equal to 4. So, then we had a total of 4 Jacobian submatrices. Now, what happens in the case of NRLF rectangular? Now, NRLF in rectangular, we define my unknown vector as E as E2, E3, En, T. So, this has got dimension n minus 1 cross 1. Then my vector F as F2, F3, Fn transpose, it has also got n minus 1 cross n, and our standard vectors P is P2, P3, Pn. This is already known, but we are just defining it. So, this is n minus 1 cross 1. Vector Q as Qm plus 1, Qm plus 2, Qn transpose T, this is n minus m cross 1. And then we also define something called vector V square, which is nothing but vector V2 square, V3 square, Vm square transpose. So, this has got dimension of n minus 1 cross 1. So, these are unknown, and these are known vectors. So, then therefore, in this lecture what we have first again recollected what is mean by this NRLF rectangular method. After that, we have derived the equations for real and reactive injected power at bus I in the rectangular coordinate. After that, we have defined that what are the unknown quantities and what are the known quantities, and we have also looked at their dimensions. So, now in the next lectures onwards, we will be again continuing this particular topic. Thank you.